Hi everyone, my name is Mohsen. This is a joint work with Ehsan and Yadollah. I'm a master's student at University of Tehran, and together with Ehsan, we'll present this work. This talk is about metaphors in pre-trained language models. Let us first discuss what is a metaphor. By the conceptual metaphor theory, a metaphor is a cognitive phenomenon that connects two distinct concepts or domains together. For example, here, it looks like our taxes are dropping as a metaphor because it contains two different concepts. We are connecting the word dropping, which is a physical downward movement, with the word taxes, which is the target concept of the sentence. Therefore, we are using the generation and creation abilities of the language to better convey our message. As you know, metaphors play a vital role in human communication and language. The creativity and problem-solving depend on the analogies and metaphors a cognitive system like our brain relies on. So, modeling metaphors is essential in building human-like computational systems. So, the motivation behind this study is to analyze and answer this question. Do our great pre-trained language models represent metaphors? And if so, is it generalizable across languages and datasets? So, to have a comprehensive understanding of metaphorical knowledge in pre-trained language models, we probe them in three different ways. These methods are conventional probing and cross-lingual and cross-dataset generalization, which we will discuss next. We employ four main datasets. Their names and examples are shown here. We first made them all binary classification problem, as LCC dataset had a score range instead of binary scores, and then we have label balanced all the datasets to get a more straightforward interpretation of the results. For cross-lingual experiments, we use LCC datasets, which includes three more languages other than English. As you may know, probing is a method for assessing linguistic knowledge in language representations. A common probing technique is edge probing, and we use it in our analysis. As you can see from the structure in the picture, we have a frozen PLM, a projection layer, and a multilayer perceptron, which is the only trainable section during training. The projection layer aggregates representations of a span of words coming from the frozen PLM. By getting the aggregated representations, the classifier determines whether the sentence contains a metaphor or not, and its quality will determine the level of metaphoricity knowledge in the representations.
Hello again, this is Ehsan and I will explain our methods and results in details. In our first method, we train and test on a dataset with multiple PLMs including Bert, Roberta, and Electra to see if they represent metaphorical information within their representations. We also leverage MDL probing for layer-wise analysis, that is evaluating the representations of each layer, which has shown to be more stable and informative in that setup. Our results demonstrate a considerable difference between PLMs and a random baseline accuracy, which indicates that PLMs do encode metaphorical knowledge, and in both measures, Electra and Roberta are shown to encode metaphorical knowledge better than BERT. This is comparable with their better performance on various tasks, achieved by having better pre-training objectives and enjoying more extensive pre-training data. Through MDL probing, we found that the middle layers, where the representations are reasonably contextualized, but not as much as the higher layers, contain the most easily extractable metaphorical information. Consequently, we came up with a hypothesis that the process of detecting metaphors is not very deep because all it needs to do is forecast the difference between the source and target domains. For instance, if you remember the starting example, taxes are dropping, we just needed to know that dropping does not fit well with taxes. There are more extensive experiments on this in the paper. In our second setup, we trained the probe on one language, for instance English, and test it on another, such as Spanish. This will show us how metaphors are transferable across languages, and do multilingual language models such as XLM Roberta, which we use here, encode them. We find that XLM Roberta outperforms its random counterpart, indicating that metaphorical information learned during pre-training can be transferred between languages. For instance, when we test on English, if we train a random XLM Roberta on English and test it on English, it will achieve 65% accuracy, whereas if we train a pre-trained XLM Roberta on Spanish and test it on English, we achieve 79%. This gap shows the capacity of XLM Roberta to construct language universal representations beneficial for metaphoricity transferability. Other languages are also included in our experiments reported in the paper. Our final method is to train the probe on one dataset and test on another, both in English. This will show how much dataset artifacts and biases affect the probing performance of PLMs. The caveat in this setup is that the datasets do not necessarily share the same idea of metaphors and may have different distributions. Our results show that in all out-of-distribution scenarios, PLM outperforms the random language model, implying the presence of generalizable metaphorical information. However, this gap is not as significant as the cross-lingual setup we discussed before. We have explained the differences between these datasets, such as the distribution of part of speech, and explained how more similar data annotation in datasets improves their mutual results. Altogether, we find that metaphorical knowledge exists in PLM representations, mostly in the middle layers, and that it is transferable if annotation consistency is maintained between training and testing data. Thank you for your attention.